Hello everyone, this is Ziqi from Beijing, China. I'll talk about the impact simulation of Starlink satellites on astronomical observation using the WorldWide telescope. These are the 4 parts I'll talk about. Mega-constellation satellites have had non-negligible negative effect on optical astronomical observation. The data polluted by satellite constellation is more difficult to process and analyze, and some are even forced to be abandoned. Satellite producers proposed several solutions, including SpaceX's methods of painting the satellite body black or adding sun visors. The former cannot reduce the reflection of the infrared band. The latter, though, does have a certain effect of reducing brightness, but the satellites are still too bright for telescopes. In order to intuitively reflect the interference of satellite constellations to astronomical observations, we developed the Satellite Visibility Simulation Module (SAS Tracker) and the Observation Simulation Module (OBS Simulator) for the WorldWide Telescope, aka WWT. WWT is an open-source astronomical data visualization software, originally developed by Microsoft Research and now maintained by the American Astronomical Society. With its powerful space-time simulation function, we can simulate any celestial phenomena. It can also display satellite orbits by loading satellite TLE data and support users to import well-known text to draw geometric markers on the celestial sphere. Based on these capabilities, we developed 2 modules for WWT to simulate the visibility of the satellite, the SAS Tracker, and the execution of telescope observation program, the OBS Simulator. This is a snapshot of how the SAS Tracker simulates the Starlink orbits. The SAS Tracker module can calculate whether and when satellites will appear in a specific sky area based on Starlink's orbital data. This is how the SAS Tracker calculates the satellite's visibility period at a given time and given space. Please note that only the periods when the sun's altitude angle is below -12 degrees will be calculated. SAS Tracker will divide the simulation period into 5-second slices and sequentially calculate which satellites will appear in the visible sky area of the site during each time slice. This requires the satellite's altitude angle greater than 0 and not be eclipsed. After the calculation of all time slices, the start and end time of each satellite's visible period can be obtained. It should be noted that some satellites may be visible twice in the entire night. Since the pointing limit of most telescopes is not below than 30 degrees above the horizon, satellites visible with a maximum altitude angle less than 30 degrees will also be excluded. Eventually, the qualified satellites will be loaded into WWT's 3D scene. Here we come to the OBS Simulator module. It can load and visualize telescope observation plan files, simulate the position of celestial objects and satellites in the telescope's field of view at a specific time. After the observation plan is loaded, WWT will mark all the observable areas on the celestial sphere with grids according to the telescope's field of view, as shown in the snapshot. Using these 2 modules in combination, we can determine when the Starlink satellites will enter which observation grids, and thus affect the observation. After this, the OBS simulator will automatically record the satellites passing through the observation grid. The module will calculate every 100 milliseconds in the background whether there are satellites entering or exiting a certain grid. In this way, whether and how the satellite has an impact on the observation plan can be analyzed. Based on the features described earlier, we simulated the impact of Starlink satellites on the Altai Observatory. The table lists the location and other characteristics of the observatory, which is still under construction. First, we simulated the impact of Starlink on the observable sky zone of the Altai Observatory during a one-year period from May 2021 to May 2022. The yellow part is when the sun is above -12 degrees. Satellites are only visible during the blue part. We can see that during May to August, there are some satellites visible during the entire night. The search for the electromagnetic counterpart of gravitational wave is a major scientific mission of the Altai 1-meter telescope, aka A1T. So we simulated the impact of Starlink on real gravitational wave events follow-up observation. This follow-up telescope is the Altai 1-meter telescope. So we take the GW190425 as an example for the simulation, whose 90% confidence localization area reaches over 7,000 square degrees. So we divided the whole gravitational wave localization sky area into observation grids that are the same area as the telescope's field of view, which is 3,868 A1T observation grids in the whole sky. Then the grids are displayed in WWT through the OBS simulator. The grids drawn on the celestial sphere will change their altitude and azimuth relative to the telescope over time. Only the grids with altitude angles greater than 30 degrees are taken as observable, and only the satellites in that area are counted when they enter a grid. Suppose this gravitational wave event occurs on May the 1st of 2022. We simulated A1T's observations of the event and counted the presence of satellites in the telescope's field of view. In the simulation, over 36% of visible satellites enters the gravitational wave observation grids on average. 40% of grids were affected and would generate trail if they were observed. On average, 1.22 trails in each affected grid is generated. From the simulation, we can see that the impact of Starlink on imaging can be eliminated by avoiding the effect observation grid, or pausing observation for a few seconds when a satellite passes through the grid. Under the typical exposure time of 60 seconds, its image on the corresponding pixel element on the CCD won't saturate A1T. In subsequent data processing, algorithm repair can be used to remove the trail if necessary. But when 42,000 Starlink satellites are in orbit, the average grids that get affected by satellites in 10-minute bin is over 85%, the maximum is over 99%, and an average of 4.77 trails will be left. It is more necessary to adjust the observation plan to avoid the influence of satellites. Based on the theme of dark and quiet sky protection, we introduced two new WWT modules that can work together to simulate the impact of satellites on the astronomical observation. The simulation tools were used to predict the overall impact of Starlink satellites on the Altai Observatory. Under the current scale, the impact is low, but when the number of satellites reaches over 42,000, it is necessary to consider their interference as an important factor in observation plans. The new modules in WWT can help observers make adjustments to mitigate these impacts, and can show the public the damage of satellites to the quiet and dark sky intuitively. The WWT guide tour titled "The Dark and Quiet Sky" will be played now. It is available at China VO Paper Data Repository. Please enjoy.
The problem of the light pollution hasn't been solved yet. An even bigger astronomical crisis is looming. Starlink, the frantic 42,000 low Earth orbit satellites. When the Starlink satellites go into orbit, they show up in telescopes around the world. They have an apparent magnitude of about magnitude 4 to 6 and even flash, obscuring distant objects intended to be observed. This is a satellite for weather observation. Starlink satellites operate in Ku and Ka wavebands and interfere with weather satellites' observations of water vapor spectra, resulting in weather forecasting inaccuracy. Radio astronomy observations at these wavelengths will also be disturbed. Gravitational wave follow-up observation is easily interfered by Starlink satellites due to its timeliness and large localization area. Wide-field telescopes use pixel grids to search for electromagnetic counterparts. The single exposure time of gravitational wave follow-up observation is generally tens of seconds. If a satellite enters the field of view, a satellite streak will be generated. According to observation simulation, the interference duration of satellites varies in different time periods. The proportion of observation grids disturbed by satellites to the total number of grid is also different. As more satellite constellations like Starlink get in orbit, ground-based and near-Earth astronomical observations will suffer more. We must take actions to protect the darkness and tranquility of the sky. The night sky without stars is like a world without flowers. We long for a starry sky at night and hope our future generations can enjoy its beauty. Protect the dark night now and make it fortune for all humankind.
Thank you for listening.